Hi, I'm Sean Gann, and this is Minute Math, and today we're learning about area under a curve using limits of sums.
Minute Math, when you need help you use Minute Math.
We're given this problem right here, the sum from k equals 1 to n of 18k, and we have to evaluate the sum. Now we've used our definitions here and apply it a little bit. Well, what I want to do here is to rewrite this. I don't need the constant 18, so if I put the constant 18 outside of the sum, we're left with 18 times the sum from k equals 1 to n of k. And so now we can see from our definition, we know the sum from k equals 1 to n of k is that n times n plus 1 over 2. So rewrite that. We have 18 now times an n times n plus 1 over 2. And now we want to simplify this out a little bit. We know the n times the n, and then n times n plus 1 comes out to be an n squared plus an n, and the 18 and the 2 simplify to be that 9. So we have a 9 out here times an n squared plus n, which then simplifies, distribute that back in, or into it. We have a 9n squared plus a 9n. And there we have it. Our final answer here is just a 9n squared plus a 9n. We're given this problem right here, the sum from k equals 1 to n of 2k plus 5, and we have to evaluate the sum. Well, first thing is I'm going to try to separate this into two sums. So, I guess I can put it right here. We have the sum of the first part, and I'm going to pull out the 2 as well. So, let's do both parts individually. We'll do it like that first. K equals 1 to n of 2k, plus the sum k equals 1 to n of 5. What does that get us? Well, like I said, we can first pull out the 2k, or the 2 part from the k here. So we have a 2 on the outside times, if I can write sum, not the letter e, sum from k equals 1 to n of a k. We're going to do the same thing with the 5. I'm going to pull it out front, and we have the sum now, k equals 1 to n, but if I pull out a 5, what's left? Just a 1. And we can see now it matches both of we had a sum for our definitions. K equals the sum from 1 and the sum of the variable k. So let's go apply that here. 2 stays on the outside, and we sum, what's the sum from k equals 1 to n of k? Well, it tells us it's an n times an n plus 1 over a 2. We add 5 times the same thing when we sum a 1, which is just the n value. Okay? So now I want to go simplify this a little bit. 2's cancel right here, and so we have an n. Let's distribute that n right now. So we have an n squared plus an n plus a 5n that's left over. Well, n squared stays there, and n plus a 5n is a 6n. And there we have it. Our final answer here for our sum is n squared plus 6n. We're given this problem right here, the sum from k equals 1 to n of 8k squared, and we need to evaluate this sum. Well, first thing I'm going to do is rewrite this to put the 8 outside of the sum. So we have 8 now times the sum from k equals 1 to n of a k squared. And now it lines perfectly with one of our definitions. So let's go put that right here. Our definitions, we have 8 times, what is k squared? That becomes a n times an n plus 1 times a 2n plus 1 over 6. Alright, that's a 2 right there. There we go. Alright. So now we're just going to do some algebra to simplify this, right? Well, 8 and 6 come out. Well, actually, wait to do it later. Never mind. Let's go multiply this out. Right here, let's do the first part, n times n plus 1. So we have an 8 times now an n squared plus an n times a 2n plus 1 over 6. Keep simplifying. Let's go FOIL, if you remember how to do that, right here. So we have 8 times n squared times a 2n is a 2n to the third. And then I simplified this, n squared times 1 is n squared, n times 2n is 2n squared, that together becomes a 3n squared, plus n times 1 is an n, over 6. distribute this out, the 8 across. So we have, and you'll see later on this actually is an important step to not just cancel out right away, but we'll see. 8 times 2n is a 16, n to the third, sorry, plus 8 times 3n squared is a 24n squared, plus 8 times n is an 8n over a 6. Now we can break them up to each individual ones. 6 goes into each part and we simplify. 16 over 6 simplifies to 8 thirds, so we have 8n to the third over 3. Plus, I'm going to break it up each part. 6 goes into 24 4 times, 4n squared. Then lastly, 8n over 6 becomes a 4n over 3. This may not look necessarily simpler than it could have been just by one big fraction, but later on this becomes important. So our final answer here is an 8n cubed over 3 plus 4n squared plus 4n over 3. We're given this sum, k equals 1, from the sum of k equals 1 to n of k squared plus 4, and we have to evaluate the sum. Well, first thing I'm going to do is break the sum up to the two parts. I have the sum from k equals 1 to n of k squared, plus the sum from k equals 1 to n of a4. I can keep breaking this up a little bit, and it's really just a 4 I'm going to change out here. We have the sum now from k equals 1 to n of k squared, because that already looks like one of our definitions here. And 4 can come outside of the sum. 4 times the sum. When we pull the 4 out from k equals 1 to n, we're left with just a 1. And now we have two parts here that line up with our definition. So let's go write that. Well, what is k squared? The sum k equals 1 to n of k squared. That is a n times an n plus 1 times a 2n plus 1 over 6. And we're adding that to be 4 times the sum of 1, which is just n. And now we just gotta simplify. Now this upper part simplifies to be distribute the n to the n plus 1 and the 2n plus 1. After you do this more, you'll get practice with it and recognize this. That's a 2n to the third plus 3n squared plus n over 6. Plus, this is a 4n. Now what I'm going to do here, I want to combine this to be one big fraction. So I'm going to multiply the 4n by a 6 over a 6. So that gives me here one big fraction, 2n to the third plus 3n squared plus n. We have a common denominator, plus 6 times a 4n is a 24n over good old 6. From there, we can combine our like terms with just the n's. We have 2n to the third plus 3n squared plus a 25n now, n plus 24n over 6. Break that up, put the 6 into each part and simplify where we can, and we have a, well, 2 over 2 divided by 6 comes to be 1 over 3, so we have an n to the third over 3, plus 3 in the 6 comes out to be an n squared over 3, or 2, excuse me, 3 divided by 6 is a 2, or 1/2, plus 25n over 6 is just a 25n over 6. And there we have it in simplified form here. Our final answer for our sum is n cubed over 3 plus n squared over 2 plus 25n over 6. We're given this problem right here. The limit, as n goes to infinity, of the sum from k equals 1 to n of n or 2 over n plus 2k over n squared. And we have to evaluate this limit. Well, first I'm going to try to evaluate the sum, and then we're going to take the limit there and see if we can take a limit to get an answer. So we have to keep writing this whole limit as n approaches infinity the whole time. Now the sum I'm going to try to break up to two parts here. Okay, now remember we're taking the limit of the whole thing, just so we're clear. I'm going to break it up so we have an n, the sum here from k equals 1 to n of a 2 over n plus another sum here from k equals 1 to n of 2k over n squared. Now with that, we'll see if we can pull apart and see how we can make it look like one of our definitions. We have the limit here as n goes to infinity of the first part. Well, we know we can bring out the constant, but we also can bring the n out front. It doesn't get affected by this sum. So we have a 2 over n, or directly affected. K equals 1 over n, and we're left with just a 1 here. plus, same thing here, I'm going to pull out a 2 over n squared to be outside of the sum, and multiply it afterwards, k equals 1 to n, and we're left with just a k. So what does that simplify to be? Well, I'm just going to put it up here, not enough room, hopefully. Equals, we saw the limit, as n goes to infinity, of the whole thing here. Now let's use our rules. We have 2 over n times the sum of 1, as just an n using our definition, plus 2 over n squared times the sum, I'm going to show you some multiplication here, like that. When we have k, and k is an n over n plus 1 over a 2. Alright? So now we just have to do some nice simplification and see what we get. The limit as n approaches infinity here. The n's cancel here, so we have a 2. Plus, now, what did I do first? I think I got rid of all that. Yeah. So this n eliminates with that n squared, the square part, and the 2's here cancel. So we have an n plus 1 over n. But I still can't take the limit yet, right? We have kind of like an infinity over an infinity here. So let's go use some algebra. Limit as n goes to infinity of 2 plus, well, this can be separated to be an n over an n plus 1 over an n. Keep on going, the limit as n goes to infinity of 2 plus n over n is a 1 plus 1 over n. At this point, I can take my limit, right? As n goes to infinity of 1 over n, that just kind of right here goes to a 0. And so we're left with the 2 plus 1, which is 3. So after all of that, my final answer for evaluating this limit is a 3. We're given this problem right here. The limit as n goes to infinity of the sum of k equals 1 to m of 5 over n plus k cubed over n to the 4th power, and we have to evaluate this limit. And really what I'm going to do is try to evaluate the sum first and see if we can take the limit there. So this limit as n approaches infinity will stay on the outside for a while here. I'm going to try to separate this sum to 2 parts. We have the sum now from k equals 1 to n of a 5 over n plus the sum k equals 1 to n, or 2n of k cubed over n to the 4th. Remember, we're going to be taking the limit of all of that. We'll keep on going. We have the limit now as n approaches infinity of, we can pull out what we can here. The constant 5 and the n here can be pulled out in front of that sum. 5 over n times the sum now, what's left over, k equals 1 to n of just a 1. Plus, same thing, what can we pull out? We can pull out a k to the 3rd power. Oh, sorry, we can pull out, not a k, the n to the 4th power right here. So we have 1 over n to the 4th can be pulled out, and then we have the sum from k equals 1 to n of a k cubed. Alright? So then from here, what we can do is we need to evaluate the sums using our rules. So because I like to write higher, let's do it up here. Equals the limit as n approaches infinity. We have a 5 over n times, well, let's just sum at 1 is just an n. Plus, we have 1 over n to the 4th here, but we have the sum of k to the 3rd power, which is a n squared over an n plus 1, all squared over a 4. I just want to make sure I get this all that I need to be simplified here and figure out how I'm going to do it, or make sure I stay on track. So simplify where we can. There's many ways to simplify this, so make sure I follow my notes. N's here cancel, and we have just a 5 left over. That's always lovely. Alright, now what I cancel next here, well, I see we have n squared. I don't like that. We have n to the 4th. Cancel that out. We have an n squared now just in the denominator. Okay, so down in the denominator we have a 4n squared left over here being multiplied, and an n plus 1 all squared comes out to be a n squared plus a 2n plus a 1. Alright, so now at this point what I'm going to do is I'm going to take this 4n squared to each part. We have the limit here as n approaches infinity of 5 plus n squared over a 4n squared plus 2n over a 4n squared plus 1 over a 4n squared. Now we can simplify this where we can. Okay, so we have the limit here as n approaches infinity of 5 plus n squared over 4n squared is just a 1/4 plus, well, the n here cancels with the squared, so we have, and the 2 and the 4 become 1/2, so 1/2, 1 over 2n, okay, plus, we have 1 over a 4n squared here. Well, from there, we actually now can evaluate the limit. 1 over 2n goes to 0, and 1 over 4n squared also goes to 0. So we're left with a 5 plus a 1/4, which is a 21 over 4, which as a decimal is 5.25. So after all of this, our limit here for our sum comes out to be a 21 over 4, or a 5.25. We're given this problem right here. F of x is equal to 3x plus 3 on the interval from 0 to 3, and we want to find the area under the curve using the given interval, and we have to use the limit as n goes to infinity of the upper sum. Well, since our function is increasing always, and specifically on our interval, our upper sum is going to be like the right endpoint. Okay, we're using there, the right endpoint. So we have to set up our limit here. Now, I have the limit here as n goes to infinity of the sum. We're summing up a whole bunch of these rectangles. K equals 1 to n. And this is where it gets tricky. Okay, I have to change my value of x to define what x value needs to be put into it. Because remember, we're finding the sum of each rectangle. It's kind of like a height times the width. And so the height of the rectangle is determined by the output here, and it's the right side of it. So I have 3 times, and I'll leave a space for what we have, whatever input here. And then I have a plus a 3. Now we need to multiply this, so this right here is going to be the height of the rectangle. We have to multiply that by what's going to be the width of the rectangle. And the width of the rectangle determines on how many rectangles we have. So what we need to do is take our interval from 3 minus 0 over the number of rectangles we have, which is going to be the n here. And so this right here is my width, just so you can see it. So we have the height of the rectangle we defined here, and we have the width as 3 minus 0 over n, which is going to be 3 over n. So what does the height need to be? We need to find the x value that plugs into that. Well, from here, we know we start at 0, okay? So we start at 0, we take our 0 value here, and we have to add the width to it, right? We add the width to that, right? Whatever our width is going to be, boom, that's the first right endpoint. So 0, so start here. First one here is a 3 minus a 0 over n, again that width. And then we have to multiply by the variable k to see for each one that we're doing. Okay? Right there. And now we set up our limit here. So now we have to go see if we can simplify this slightly and then evaluate the limit. So we have the limit here as n goes to infinity of n sum k equals 1 of this inside. How much should I simplify that out? Well, 3 minus 0 is 3 over n times k is this 3k, or 3 over n times k. So we have here a, well actually here, this becomes, so I save some space here because I think I'm going to need a lot of it. That's 3 over n, right? So 3 over n times that 3, and the k here comes out to be a 9k over n plus 3, and we're multiplying that all by the width on the outside here. Okay, the width on the outside. I want to make sure I'm just make sure I have everything lined up here. Oh yeah, extra parenthesis. That's why. I was wondering. It's like I knew that needs to be on the outside. 3 over n. I forgot that extra parenthesis over the whole thing. Apologize. Okay, because that's the height times the width. Got it right here. So now let's keep simplifying this out. The limit as n approaches infinity of the sum from k equals 1 to n. Now let's go multiply this 3 across the board here where we can. Okay, so 3 times the 9k over n here. We have the 3 times the 9. Did I do this right? Yeah. Sorry, oh my goodness, I'm flipping things around. 3 times the 9k is a 27k over n squared. Plus 3 times 3 is a 9 over n. So I got flipped around because I actually flipped this around. Okay? So to simplify this out one more time, before we take the limit as n approaches, or the sums, I'm going to break this to be two different sums, and I'm going to reorder it and put the 9 over n first here. So to do that, I have the 9 over n, I'm going to put that one first, k equals 1 to n over 9 over n plus the sum k equals 1 over n of 27k over n squared. Okay. Now hopefully we have enough room here, I think we will. The limit again, as n approaches 0, we can pull out that 9 over n out front of our sum. So 9 over n here times the sum from k equals 1 over n. And what's left is just the 1, it looks like our definition. Same thing here, we're going to pull out the 27k. 27k here times the sum k equals 1 to n of just 1 over, we pull out the n, not the k. See, I always do this. It's okay, we all make mistakes, right? Bear with me if you're one of the few viewers of this video. Pull out the n squared, so 1 over n squared, and we're left with the sum from k equals 1 to n of a 27k. Or pull out the 27 as well. See, once you get a little flustered, you mess up a little bit. It's okay. So 27, see up here, and we have a k. And that's also, I hate writing down low. Let's go simplify this out. Now, this limit is of everything, just so we know here. Okay, don't forget to take a limit. It's easier right up here. Limit as n approaches infinity here. Well, we have a 9 over n times the sum of 1 is just going to be an n. Plus, we have 27, if you can see it, over n squared, right there. And the sum of k comes out to be that n times an n plus 1 over a 2. And now we have to simplify all of this, okay? So we have the limit here as n approaches infinity. The n's cancel right here, and we have a 9. Plus, well, we have this n squared canceled with that n here. And so we have if it's easier to see, we have 27 distributed across to both parts. 27 plus n plus a 27 over a n or a 2n right there, okay? Well then from here, okay, we can break this apart to two fractions again. So we have limit as n approaches infinity of 9 plus, well, 27n over 2n plus 27 over a 2n. We need to be able to take the limit, and the n's cancel here, and that's fantastic. So now we have the limit as n approaches infinity of 9 plus 27 over 2 plus 27 over 2n. And at this point, we can take the limit, because we have n just in the denominator as we go to infinity, and we know this will go to 0. So we're left with our constants, 9 plus 27 over 2, and 9 plus 27 over a 2 comes out to be a 45 over 2, which is equal to 22.5. So after all of that, and bear with me, sorry for the mistakes out here, but it's all good, we got there. Our final answer here is a 45 over 2. We're given this problem right here. F of x is equal to x squared plus 5 on the interval from 1 to 3. And we have to find the area under the curve using the given interval, using the limit as n goes to infinity of the upper sum. Okay? So first thing I want to note is on our interval from 1 to 3, our function here is increasing. Okay? So the upper sum is going to be like a right Riemann sum. We're looking at the right part of the rectangle for the height. Keep that in mind. So let's go set this up as a big limit here. The limit as n approaches infinity of a sum as k, oops, not k, n, k equals 1 to n and this is where we want to plug in our function for x. Now remember, this rectangle here, the rectangle we're using for the function here, the height of the rectangle, right, each area of the rectangle is the height times its width. The height is determined by the output of the right of the sum here. So the output is determined by an input that goes into x. So I'm going to leave a space where the x is. Squared plus 5 right here. And this here is going to be the height of the rectangle times, we need to find the width of the rectangle, which is at 3 minus 1 over the interval, 3 minus 1 over the number of rectangles we have, which is n. And so you can see it, this is the width of the rectangle. Now we're looking at the right sum, right? The right value of each rectangle. And so we need to start at our first value, 1 for the x. It's going to go in here. So the first left endpoint of all of our function intervals is 1, but we want to find what is the input value of the right rectangle right on the right there. If you see like this curve kind of looks something like this, right? And it's going boop, boop. And we have rectangles here for each one. If you can see, well, that's what's upper sum rectangles actually, like this. If you can see, it's like so small, but we want to find that right value. So if this is 1, we want to find what's the value right there. We add the width to it. So 1 plus whatever our width is, okay? And the width is at 3 minus 1 over n, so that gives us the width of the first one, but we still have to have the variable k here, so we can keep adding it. And now we have a limit that we can, well, solve here, really. So I think I simplify this out first for a little bit. So we have the limit as n approaches infinity, gotta write all this stuff out. K equals 1 to n with a sum here. And we gotta simplify, how far do I simplify in this? Well, that becomes a 2 over k. Oh, I simplified pretty far in here, okay. So we have a 1 plus, this becomes a 2, so 2 over n k squared plus 5, and then all of that becomes multiplied 2 over, and not much simplification there, but it's our limit as n approaches infinity. We can take our time. N over k equals 1 times, we have to multiply this 1 plus 2 over nk, we square that, right, and simplify that, and that comes out to be, I won't bore you with that, that is a 1 plus a 4k over n plus 4k squared over n squared, and we're adding a 5 to that and still multiplying 2 over n, okay? Well, adding the 5 should be pretty easy here. The limit as n approaches infinity of n over, or sorry, sum of k equals 1 to n of 5 plus the 1 gives me a 6. So it's 6 plus a 4k over n plus 4k squared over n squared, multiplying that by a 2 over n. Alright, distribute that 2 over n to all parts, and what do we get? Well, let's go, yeah, I'm going to do it up here because I'm going to need that space later. We have the limit as n approaches infinity of the summation, k equals 1 to n, multiplied to all parts, and do I have a simplified step, so I just make it easier for myself here. No, I left it as that. Okay, 2 times 6 is 12, so we have 12 over n plus, simplify that, multiply out 2n times a 4k over n is a, ooh, don't lose my spot here, okay. Is an 8k, see I wrote my notes wrong for a second, 8k over n, that's what's confused, plus multiply 2 here of an 8k squared over n to the third power, and this is an n squared down here, okay? Alright, so we have this big sum that we need to take here. Let's use our rules, and hopefully I have enough room here. Alright, our rules here to really multiply that out. I'm going to kind of skip a step here, kind of show it all out, but we have the limit here as, I'm putting multiple sums, as n goes to infinity. We're taking a limit of each one, and I'm going to pull out within that step what we have. So I'm going to limit the first part here. I can pull out the 12 over n. So I have a 12 over n times the sum from k equals 1 to n. And what's left is just the value 1. Plus, same thing here. I'm going to pull it out at 8 over n squared. And we're left with the sum from k equals 1 to n of just a k. Plus, here again, same thing, I'm going to pull out an 8 over n cubed. And we're left with just a sum, oof, that's a bad sum, k equals 1 over to n of k squared. Just barely. Alright, hopefully you can see that. But basically I'm separating each one of these out, and I'm left with stuff from our definition here. So again, we're taking the limit of all of that. If you need to see that bracket there, there it is. The limit here, as n approaches infinity, we have a 12 over n multiplied by 1 just comes out to be an n, plus an 8 over n squared, multiply k, turns out to be that, using our definition, n plus 1, over 2 plus 8 over n to the third power times k squared is that good old n times n plus 1, 2n plus 1. Oof, just barely got it in there. Over 6, don't forget that. Oof, okay. A lot of simplification here, so let's bear with me. N's cancel right there, pretty easy, so we have the limit here as n approaches infinity. We have a 12 going on there, okay? Now, did I cancel that out ahead of time? I think I did. How much did I cancel out? Well, we'll find out. I distribute, the 2 and the 8 goes to the 4, and I actually multiplied this out. This was like a tricky part for me here. Multiplied the n squared and n cancel out, distribute the 4, and so we have now plus a 4n plus 4 over an n right there. Okay, right, so 4, the n squared and n cancel by n here, 4 distributes to both parts, 4n plus 4 over n, plus, I'm going to do the same thing with the 8 here, okay? So the 8 and 6, what do I have 8 over 3n squared? Oh, that's why. Okay. So to simplify this, I actually multiplied all of this out. Well, I cancel out the n cubed and the n here. So I have the 8 right here. Oh, and multiplied all that out. That's why. Okay. So I multiplied all that out, and I have a 8. So the n plus 2 plus times the 2n plus 1 times the 8 comes out to be an 8n squared plus a 12n plus 4 over a 3n squared. Let me just make sure that 6 got canceled out here, actually. Sorry, that's what it was. 3, just gave me 4. Multiplied all that out. 4 times n plus 1 times 2n plus 1 gave me this 8n squared plus 12n plus 4 over 3n squared. So now we gotta keep simplifying here. It gets a little easier because we can't take the limit yet. Okay? And hopefully you're good with simplification. Clearly I make mistakes. It happens sometimes, you get lost in your space, but it's a free video. 4n over n simplifies, and break this up, and I have, well, the n's cancel, I have a 4 plus a 4 over n. Fantastic. 8n squared over 3n squared becomes just an 8 thirds. 3n squared goes in that one here. Over 12n squared, well, we have a 4 in the numerator over just an n. We divide that. Simplify, it's an n, plus a 4 over 3n squared. Alright, did I get everything I needed here? 12n over, oh yeah, okay. 12n over, make sure I have the 16 there, 8 thirds, 4 over n, 4 over n again, or 12n over 3n, or 12 over 3n, which I have, okay. Plus a 4, okay, great. Either way, now we can take the limit. This here goes to 0 with the n in the denominator. This goes to 0 with n in the denominator. This goes to 0 with n in the denominator. And we're left with a 12 plus 4 plus 8 thirds, just a constants when we take the limit. And we add all those up, and I did it for you here, 56 over 3, which is equal to an 18.6 repeating. Glad this problem's over. So our final answer, I'm sorry for the little, I don't know, tight work. Hopefully you can zoom in. Upgraded the camera for that. So our final answer here for the whole upper sum, or n goes infinity of the upper sum, is a 56 over 3. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.